Okay, so we are going to get started on Module 3 today. Module 3 is all about velocity analysis. So as we look at our learning plan here, you're going to find that we have two PowerPoints. So this evening, we're going to be going over part 1, and then we'll continue on the next time we get together with part 2. And then we're also going to be working through the handout that you see here. So if you happen to be virtual or not in the classroom with me, then make sure that you download that and print that off because we will be working through that. That's actually going to be your practice problems, part of your practice problems that you're going to be handing in. So it's just kind of easy to fill in the blanks that I have there. So, so what we're going to do is we're going to get started by looking at our PowerPoint part 1. I'm going to zoom out here just a little bit. And this is going to coincide with chapter 6 in your kinematics textbook. So first part of the lecture here. So our objectives in chapter 6 here are going to be, first of all, defining linear, rotational, and relative velocities. Some of these things you've come upon in other courses that you might be currently taking or have taken in the past, like physics is kinematics is an application of physics. So we end up seeing a lot of parallels there. So some of these things are going to be items that should be review. If not, that's okay. And then others are going to be continuing to build on those that you have heard before. We're going to be looking at converting between linear and angular velocities. We're also going to be applying the relative velocity method to graphically solve for velocities of a point on a link. So when we say graphically solve, you can imagine that we're going to be using AutoCAD for these problems so that we get nice, accurate numbers. And then we are going to be doing some, if you would, math along with it, but we are going to be actively using graphical methods as well. And then we're going to use the relative velocity method to also graphically solve the velocity of a point of interest on a floating link as well. So, introduction. So, in this chapter, we're going to be looking at and answering how fast are certain points on a link traveling. Up until this point in our kinematic analysis, we've number 1 represented a mechanism in simplified form that we call a kinematic diagram. We've also moved it around and we've kind of determined based on a driver changing its position, what happens to the rest of the links that are going to follow along. So we've looked at position and we've looked at displacement. But now we're crossing over and we're going to start looking at how fast. We're going to be looking at the motion. Remember, kinematics is all about position and motion. We don't do anything with forces in here. All right. So we're just now going to be looking at the motion part of things. So the determination of velocity of a linkage is the purpose of this chapter using what we call the relative velocity method. Okay. And we're going to be graphically using that method. So let's start by looking at linear velocity. And like I said, this should be a subject that you've heard and studied before. So linear velocity V is the straight line displacement of a point per unit of time. So velocity a lot of time is going to be looked at as dividing the amount of distance that you cover divided by the amount of time it took you to cover it. So we'll say in this case, we have V is called velocity. Maybe those units are in feet per minute. Then it would be equal to, if we wanted to calculate it, how much distance or displacement occurred. So R, in this chapter they use, or in this textbook, they use R for displacement or distance. And in this case, the units would be feet if we're going to end up with feet per second, and then divided by the amount of time. So units of time, in this case, seconds. So you'll notice that velocity is going to be calculated magnitude-wise, taking distance divided by time. Now, velocity is a vector. I know that you've heard this before as well. So because it's a vector, it needs 2 things to fully define it. It needs its magnitude and it needs its direction. Now, when we're talking about speed as opposed to velocity, speed is just the magnitude portion of velocity. That's all. It just means that we're not worried about direction. So if we look down at the speedometer in our car and we just look at how fast we're going, that's our speed. But if we're wondering, okay, we're going 50 miles an hour and we add direction to it, north, then that means it's now crossed over to be a vector. That's the only difference between them. Calculations in calculating the magnitude for both speed and velocity are exactly the same. It's just then velocity becomes a vector when we add direction. Before I move on to that, before I move on from this, velocity, because it's a vector, is going to be represented with a line with an arrowhead. We studied and looked at adding, subtracting, and using vector equations in chapter 3. We're now going to be applying them in this chapter, and the vectors we're going to be looking at are going to be velocity vectors. So the first type of motion here that we're going to talk about is rectilinear motion. And rectilinear motion just means that we're going in a straight line and we're covering a distance. That's it. It's just a straight line distance. So to calculate the velocity of something that we know that's going in a straight line, it's really easy. We look at what is the distance that we've covered and how much time did it take us to do that. So if we look at example 6.1, which is in our book, this is the first example we're doing as part of our practice problems. So for this one, we're just going to be writing out the work here, okay? So example problem 6.1. So you want to start off by example 6.1, okay? And it says here, crates on a conveyor shown in figure 6.1 move towards the left at a constant rate. Okay, so they're not speeding up, they're not slowing down, they're just going at a constant rate or a constant velocity. It takes 40 seconds to traverse the conveyor. Determine the linear velocity of the crate. And oops, I didn't catch this, to traverse a 25-foot conveyor. Okay, so what we want to do is we want to determine what is the velocity of that crate. So they've shown a crate, they have on a conveyor, okay, they're showing the velocity vector pointing to the left, and we want to know what is the magnitude of that velocity vector, or what is the speed, if you would, that this is going to the left. So to determine that, we're going to say V is equal to R over T, okay? I think they use capital R, I'm sorry, capital R over T. Now, in this case, V is going to be equal to velocity, okay? And we're going to be solving for that, all right? So that's going to be a quantity that we're going to solve for. R, in this case, if we look, R is distance. So you'll notice that they give us a distance of 25 feet, right? So this is going to be 25 feet. And then T is going to be the time that it takes for this to cover 25 feet, and that's going to be 40 seconds, okay? So now as we can see over on the left-hand side where we've got our equation, velocity is equal to R over T. When you write your equations out, my expectation is, just like it was in statics, most of you had me for statics, that we write out our equations so that when we have something that is a division, we want to write the denominator on the top and the numerator on the bottom. Wait, yeah, not, why am I saying it? Numerator on top, denominator on the bottom, right? Shoot. I'm like, no, that wasn't right. And I couldn't get it. So, okay, numerator on the top, denominator on the bottom. So we want top, bottom, so that we can see when we add our units to this, that we can easily see the cancellation. Okay, don't write this, do not write this, R is equal to T, R divided by T. This is not acceptable. I will not accept that. Okay, so we want to do top down fraction, So I have my equation in variable form. You always have to show your equation in variable form. Then what we're going to do is we're going to put our values that we know. So we can say, okay, R is 25 feet divided by 40 seconds. So now we're simply going to take 25 divided by 40. And it is going to be 0.625. And now our units. Notice as we look from top to bottom, there was no cancellation. So this is feet per second. So this is going to be feet per second as the units. And then we're going to put a box around our final answer. Make sure you identify the variable of your final answer. So don't just put a box around 0.625 feet per second. I want you to identify V is equal to. That's what you're solving for in the equation. Okay? So this is this would be your example 6.1 for your practice problems. So you can set this aside and it's just the work right here. No diagram, no AutoCAD or anything like that to do. Okay. So let's get back to our PowerPoint. So my assumption is velocity like that, calculating how fast something is going is probably a pretty straightforward problem that you can do. Now, what we're going to do is we're going to be looking at that velocity handout that I referred to. So for those who are in the room, I already made the copies of this. For those who are virtual, you are going to want to have this printed out, and hopefully you're able to do that. I'm just going to peek back at, at our module, and I just want to show you exactly where that's at. That's in our learning plan here, as I referenced earlier, and it's going to be the Kinematics Chapter 6 Velocity Handout PDF. Okay, that's what I've got underneath my camera. I'm going to go back into the part 1 here, get us back to where we were. And then we're going to go underneath our camera. Okay. So this is the handout that we're going to be referencing then for the rest of the class tonight. Okay. So, what I developed this handout, as you can tell, and I did it because I feel that our book is kind of light on this stuff. I used to teach physics, so this was kind of part of one of the physics units that I did. And what was nice about me teaching physics is I could tell my students, or when they came to kinematics, I could be like, I know we already covered this, so I didn't have to really go over it. It was just an overview. But I don't teach physics anymore, so I want to be sure we're all on the same page. So I'm going to be using this handout to just dive a little bit deeper than what the book does to make sure we have a good understanding of these relationships and the units and how to get there in all of the cases. So first of all, we already talked about linear velocity. Linear velocity is going to be distance divided by time, as we just had looked at. So a conveyor belt, a car moving down the road, a person walking a distance. We can figure out how fast they're going by simply taking the distance that they cover divided by the amount of time it takes to do that. Another variable that's popular for distance is also s. So you might see that in other contexts as well. As we move down the handout, the next one here, the next area here is velocities of a single rotating link. So if we have a single rotating link, so we've talked about links in mechanisms. So for instance, if we have number 1 here as our frame, and then we have our link number 2 here. It's just a straight standard, link that is, a common whatever. It's just a distance thick. And along that length, it's not connected to anything else. So as we look at that single link, number 2, rotates at an angular velocity W2. So this lowercase omega, it's the Greek symbol, is going to be the symbol that we see universally for what we call angular velocity. Now, angular velocity, you're going to notice that we have W2 here. So W2, it means it's the angular velocity of link number 2. All right. It's giving also a direction of rotation. As we can see here, the arrow is showing that this is rotating in a clockwise direction. Okay. So angular velocity W is how fast a link is moving at a rotational speed. Okay. Now, the rotational speed units that would be given for W are going to be like revolutions per sec or revolutions per minute. That's a very common one. So for instance, if you want to order a motor and we want something to go, 1700 RPMs, that's what W is. W is an angular velocity in revolutions per minute. How fast are we rotating about, in this case, a fixed center? Now, you're going to notice that we have positions X, Y, and Z along the length of that link, okay? You're going to also notice that at each one of those points, there's a velocity vector, okay? So remember, velocity is a vector. We need both magnitude and direction. So we can represent it as a vector, a line with an arrowhead. So you'll notice here at point X, we have a straight line velocity V. Okay, a rectilinear velocity from above, that's V, rectilinear, so it's going in a straight line. and it is going to represent the velocity at point X. Then you're going to notice we have the very same thing for point Y and point Z. Something you'll notice, first of all, about the directions of those velocities is that those velocities are always going to be, number one, pointing in the direction of rotation. So since W2 is going clockwise, notice that's also the direction that these are pointing. Okay, the direction that we're rotating. If we were going counterclockwise, if this was pointing this way, these would be going up and to the left, but they're all going down and to the right. Do you guys see that? You'll also notice that they are always perpendicular to the radius of rotation. So the orientation of that velocity, if we take and we find from the center of rotation and we draw a line straight to our point, our velocity is perpendicular to that. So you'll notice that I have that 90-degree symbol that's there. Okay, so velocity vectors are always going to be consistent or point in the direction of rotation, and they are going to be direction-wise perpendicular back to the line or the radius of rotation. Okay. Now, the relationship that exists between angular velocity and straight line velocity have to do with how far those points are from the center of rotation. So the base equation we see right here, velocity, straight line velocity, we'll put a little tail on there. That's how I always show lowercase v, is going to be equal to omega, angular velocity, times the radius or the distance that point is away from the center of rotation. Okay. I hope everybody's listening as we go along. I go into detail on this because this is not in the book. Okay. So please follow along. So these are the relationship here on the front page. We can go back to this in some examples that we have coming up, but this is kind of like, you know, how things are. Now on the next part of the page here, the next page, we're going to be looking at units and converting. Now, units are huge, okay? If you had statics with me, we were big on units. You have to write out your units in every phase of the problem. And the reason we do that, and I hope you use this in other classes that you're taking, specifically like physics. This is like a perfect application. If you know what the units are that you're expecting to get at the end of a problem, and you end up with them, it means that you set everything up properly, because if you cancel out those units throughout the problem and you end up with the correct units, you know you set it up correctly, and 99% of a problem is set up, okay? Hoping, you know, you should get the right answer or very close to it if you put all the numbers in place, but getting the final units to work out and cancel properly, you will have confidence in how you set it up. So I emphasize units, okay? So first of all, we got to know what units we're expecting. So when we have straight line velocity v, what are the units that we would have here? Now this horizontal line here is depicting like a numerator, denominator, top, bottom. So what would our units for velocity be? Just tell me what you think some units are, and I'll open up the chat box. You can put it in here as well. Meters per second is one. What other ones? So distance divided by time. What else? Miles per hour, feet per second. I like it, Jack. Thank you. Any others? Kilometers per hour. Absolutely. So anything that would be distance divided by time. I'm going to put in inches per second, just because those are going to be kind of the units. Millimeters per second, inches per second are very common. Our book is predominantly, I think almost exclusively, oh no, there's been some metric, but the majority are going to be our English. So now using kind of bouncing off of that for our inches per second, the next one is going to be radius or distance. So what are appropriate units for radius or distance? Feet, inches, miles, yes, anything like that. So we'll just stay consistent with inches here. Okay, so as part of what you're going to be handing in, I am going to be looking that you have these fill in the blanks done. Okay, so that's going to be, this filled in is your practice problems, okay? Or a majority of it. Angular velocity. What are we expecting for angular velocity? revolutions per minute or radians per second. I'm going to put in radians per second because we are always going to be in and out of that equation. V is equal to W times R. W always has to be in radians per second. You probably have experienced that from physics, right? Yeah. Good, 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 good. So when we look over here, here's the equation. This is the rearranged V is equal to W times R. So this is our base equation, the one that's most often referred to. But if we rearrange it to solve for W, we'll simply get V over R, or velocity divided by its radius or its distance from the center of rotation. So units wise, anything that are in these like little square brackets, those are always referring to units, not numbers or variables. So if we look at the units here and we use inches per second on top for velocity divided by inches, okay? So fill that in, inches per second divided by inches, because these are the units for velocity, okay? And these are the units for distance. When we do that, not worrying about numbers, just looking at units, you're going to notice that inches and inches cancel out. And we end up with nothing per second. But do we? We actually end up with radians per second. So when we're in, I like to call it the rotational world, when there's nothing per second, we insert radians. I like to say they magically appear. And then they magically disappear sometimes too. So they're kind of like lucky charms. Did you get it? Anybody get it? Oh, tough crowd. I know. For years, I've referred to radians as lucky charms, that they magically appear and they magically disappear. It's an easy way for me to remember. So anyway, so when we have inches per second divided by inches, we end up with radians per second, not nothing per second. Radians are going to appear. Now, when we are using W, we know that usually, for instance, in any problems that we're going to be looking at, our W, for instance, on a driver link is going to be given to us in revolutions per minute. Okay, revolutions per minute. But we can't use that in our equation because we always have to have it in radians per second to be able to use it in an equation like this. Okay, so what I want to do here is I want to practice a little bit converting between revolutions per minute and radians per second, and then radians per second to revolutions per minute. Now, the way that I'm going to show you here is the way that I'm expecting to see it in the work that you submit for kinematics. So if you're not listening to me right now, come back to me, because I don't want anybody to say on the assignment, I didn't know I was supposed to do it like that. I am very particular about conversions, okay? Like I said, units are everything. And if we get our conversions right and we end up with the right units, we know that we can have confidence in our process and our numbers. So we are going to be using what we call the ratio method for converting. Now you're going to notice that our first problem that we're going to go from 500 revolutions per minute to how many radians per second. So we're going to want to convert that to radians per second. Now, when we start out with RPMs, it's fine to call it out as RPMs, but when we're doing a unit conversion, we need to expand that into revolutions per minute top bottom. So it's revolutions on top and per minute on the bottom. And our 500 is like a fraction over 1. Okay, we know that to be the case for whole numbers. So now what we're going to do is we want to convert that. So you're going to notice that next to it in these two like vertical line brackets or parentheses, if you would, we are going to be identifying our conversion. Now, what we need to do is we need to get revolutions into radians, and we need to get minutes into seconds. Now, there's a lot of different conversion tables out there, and it might say, oh, if you want to go from revolutions per minute, you just multiply by blah, blah, blah to get radians per second. I am not accepting that. I'm not accepting that. You're going to write these out every single time, all right? And I want to make sure they're correct, because those charts it's easy to transpose a number. It's easy to divide instead of multiply or whatever you're going to do. By writing it out using this ratio method, you will get it correct every time. Okay. So I'm going to start by converting my revolutions first to radians. Now I'm going to be multiplying across the top here and dividing by the bottom. Because I want revolutions to cancel out, one revolution is going to go into the denominator in our first ratio. And directly above it, we're going to put how many radians are in one revolution. In one revolution, or 360 degrees, there are 2 pi radians. Okay. Again, you're writing this out exactly like you see here because this is what I'm looking for, not only in this handout, but in the application that you're going to do for the problems for me. So I want to be sure you got it. Okay. Now, as we look here, you're going to notice that if we multiply across the top, divide by the bottom, revolutions cancel. So right now, as we look at the units that are not canceled, we have radians per minute, but we need to get into radians per second. So now since minutes is on the bottom because you wrote it out as a numerator denominator and not as RPMs, it's in the bottom here. So that means for it to cancel out, I need to put a minute on the top. And I'm going to say 1 minute, and then directly below is how many seconds are in a minute. And that's going to be 60 seconds. So I can cancel out minutes here then. And I have radians on top, seconds on the bottom. So I'm in radians per second. Okay. So now I'm going to multiply across the top 500 times 2 times pi. And then I'm going to divide by 60. What do I get for a number for radians per second? 52.6. 52.36. Okay. How many have seen that version of converting units before? Josh has, Jason has. Good. This is how you're going to be showing it for me all the time. All right. You'll never get it wrong. Like I told you, I've taught this. I've taught physics before, and I've taught this for many, many years. Or I've taught physics for many, many years. And physics was a course that was offered for a number of different program areas. So not only mechanical design was in my physics class, but I had like electronics, electromechs, and then also nuclear students. And their instructors in their program did not require this. So at the beginning of physics, I would tell them you have to write it out like this. And they didn't like it. They just wanted to kind of jump to the answer and, well, nobody else requires us to do this. And I explained to them, you're going to feel more comfortable with setting things up when your units cancel out and blah, blah, blah. And as the year went on, they started asking and they started telling me that once they started applying this in other classes, all of a sudden other things made sense. And when you do get the units right, you start to see the relationships develop. Or if you know the final units that you need to obtain, sometimes you can figure out what the equation has to be. Okay, which is going to be on top, the bottom, or multiplied or divided. So, so it's really powerful to be friends with units and unit conversions. All right, let's go in the opposite direction. Let's go from radians per second to RPMs. Okay, because when we use this equation above to calculate our angular velocity, you will not leave it in radians per second as a final answer for me. You will always convert it to RPMs. And the reason for that is because, especially on a driver, if we're going to be specifying something like a motor, you're not going to order a motor in radians per second. You're going to order a motor in RPMs. Or if you're trying to discuss, a quantity with somebody, nobody relates to radians per second. It's RPMs. You get a feel for it. So final answers will always be in RPMs. So we're going to do that very same work here. So we're going to convert our radians first to revolutions. So since radians is on top here, and that's why we don't do a slash either. So you're not going to ever write this radians per second and do a conversion next to it. I will not accept that. It has to be top bottom, numerator denominator. Okay, just like this, because then you're going to expand this out so that you can see it. If you do it like this, again, what are you dividing? What are you multiplying? How do you know? You don't see the conversions here then, okay? So I know that there are 2 pi radians in 1 revolution. So notice that radians goes on the bottom, so that when I multiply across the top, divide by the bottom, the radians cancel out. Now I'm in revolutions per second. Since seconds is on the bottom in the denominator, I'm going to put 60 seconds on the top is in 1 minute. So seconds cancels out top to bottom. And now what I have left over that I haven't canceled is revolutions per minute. You can write this as RPMs. I don't care about that, all right, as your final answer, but you have to write this out so that you can see the revolutions per minute happen. So if I multiply across the top, 10 times 60 divided by 2 divided by pi, what do we get for revolutions per minute? What is it? 1.047. Did anybody else get that? I don't have it in front of me, honestly. Can we confirm? 1.047. Anybody else get that value? I hope you guys are following along. 10 times 60 divided by 2 divided by pi. I don't have a confirmation, so I'm not confident. 95.5 revolutions per minute. Okay. Let's see. Anybody else get 95? Okay. Sounds like, well, that's why we check it, 95.5. And I don't have the answer key in front of me because you guys all have calculators and this isn't that hard. Good. Did you get the same thing, Jason?
Yeah, I just did by 3.4.
Oh, that's okay. Oh, okay. No, yeah, that's fine. Nice and close. Okay. All right. Yeah, so make sure that you can get that answer. Make sure you show these written out. Make sure you show the cancellations. I look for that. If you don't do that, you don't get points, okay? And remember, practice problems are 0 or 10. Nothing in between. All right. So let's go to our next page. So this was page 2. Now we're going to look at page 3. So here's our first example. And we want to determine the straight line velocity of point B as line 2 rotates 100 RPMs counterclockwise. Okay, counterclockwise. So you're going to notice that we have a link here. Link number 2 is attached to our frame number 1. Center of rotation here is going to be point A. It's telling us that this link or this line, that point B is on the end of, rotates at 100 RPMs counterclockwise. So that means that this whole link is rotating counterclockwise like this, okay? So show that arrow. You're also going to label that arrow W2, okay? That is the omega or the angular velocity of link number 2. Every point along link number 2 is rotating at 100 RPM. So we know that W2 is equal to 100 RPMs. Units for angular velocity are either radians per second once they're converted, or it's the RPM. So 100 RPMs is our W2 here. We will be converting it into radians per second, but for right now, variables from the problem, that's what it is. Now, we want to calculate the straight line velocity of point B. So we want to find VB, okay? We want to find VB. Now, the equation that relates the items on a rotating link are from the first page here. V is equal to W times R, okay? So we want to find velocity of point B. So straight line velocity of point B is going to be equal to W. This is actually going to be equal to W2 because point B is on link number 2. Link number 2 is the whole thing, and that entire this entire thing is going around at 100 RPMs. And then we're going to multiply that by, we're going to call it RB, because this is going to be the radius from the center of rotation to point B. Okay. Now, if we look here, we're going to just insert our values, right? So W2 is 100 revolutions per minute times my radius of, on the diagram here, it's 10 inches. And then, oh, I got to draw it up here too. So let's take time to draw our velocity of B. So our velocity of B, you're going to notice this is rotating in a counterclockwise direction. So remember, it's always going to point in the direction of rotation, perpendicular to its radius back to the center of rotation. So this is going to be velocity of B right there. Okay, 90 degrees. Back to our work here. So you'll notice here, it's a very simple equation. We're just going to take that 100 RPMs and we're going to multiply it by 10. Okay? Or do you see something wrong? Can I multiply the 100 revolutions per minute times the 10 inches? I cannot. I cannot. Remember, from page 2, I've got to have my W in radians per second. Okay? I cannot insert directly RPMs. So erase that. Okay? Erase that. Now, I can add the conversion right in here, and I'll show you how you can do that. So I'm going to take my 100 revolutions per minute, and I am going to do my conversion, my two-step conversion, to get it into radians per second. I'm going to do that right in the problem here, okay? So I know that 1 revolution is equal to 2 pi radians. So my revolutions will cancel. And I know that 1 minute is equal to 60 seconds. Minutes cancel. So notice along here, the only thing I didn't cancel out is radians per second. Okay. And then I'm going to multiply that by 10 inches. All right. You could do the conversion ahead of time and then just use the number in radians per second with its units in the problem, or you could just show the complete conversion right here inside. And you know that this is conversion because it has the vertical lines instead of parentheses. Does that make sense to everybody? Okay, you've probably seen this in other places as well. So what is my velocity of B? I'll take 100 times 2 times pi divided by 60 and then multiply that by 10. What do we get for our number? 104.72. Is that what you got? Anybody else get 104.72? 104.72. Okay, I got 2 people. So, and then as we look at our units, right now we're in radians per second times inches. Remember, when radians are multiplied by something else, they magically disappear, right? So this is not radian inches per second. This is simply inches per second are going to be the units. Okay. And then we're going to put a box around your final answer. Remember, you always show the variable equal to your number with units. Let's review the elements I'm going to be looking for here. So when you're handing in any problems, notice that in the diagram up here, I identified my straight line velocity B perpendicular to the radius of rotation in the direction of rotation. I identified my angular velocity, W2, going counterclockwise. Then as far as what we're solving for here, we're solving for straight line velocity, VB. I write the equation in variable form. So I want to see VB is equal to W2 times RB, okay? And I want the subscripts here. VB says this is the velocity of point B, so I better see a point B up here and a velocity identified. W2 is the angular velocity of link number 2. RB is the radius from the center of rotation to point B. Okay, don't just put V is equal to WR. Get used to putting the subscripts so that they match up with links and points. Okay. And then as you write everything out, all units have to be in all phases. You cannot say 100 times 2 times pi divided by 60 times 10 with no units. Not accepted. Okay, you won't get any points. I don't care if you get the right answer. Don't care. And then you sneak in the units. I'm not going to accept that. You have to put the units in all phases. You need to see whether you convert first or you convert in the problem like we did here. I want to see everything labeled and cancel. Okay. Any questions on example 1 right now? All right. Let's look at example 2. Example 2 says determine the angular velocity of link number 2. So link number 2 this time, you're going to notice has attaches between points A and B. A we can see is the frame, so that means that A is not moving. So when we look at the angular velocity of link number 2, we want to put a W2 on here. Now, it didn't tell us if it was going clockwise or counterclockwise, but there's a hint for us. We have a straight line velocity. This would be the velocity of B is equal to 250 inches per second. Notice that it's going down and to the right. It's always going to be perpendicular to its radius back to its center of rotation, but it also is always going to be in the direction of rotation. So our W2 is going to be clockwise this time. So make sure you draw it on there clockwise, and our hint is given by the direction of the straight line velocity. Now, we need to solve for W2. That's our unknown here. Determine the angular velocity of link number 2. So we know that W2 is going to be a rearrangement. If you got to go back to the first page, this is our base equation. So W by itself would be V over R. Okay, so that's going to be V over R. So this is going to be the velocity of any point on that link. So the only velocity, straight line velocity we know on this link is the velocity of point B. And then the radius, or the distance from the center of rotation to that point, is going to be the radius to point B as well. So it's the angular velocity of link number 2 is equal to velocity of B divided by the radius to B, or the distance to B from the center of rotation. Okay. So now we're going to insert our values here. So we know our velocity of B to be equal to 250 inches per second divided by 15 inches. You'll notice that top to bottom, the inches cancel out, and I'm left with radians per second. It magically appears, okay? So as far as our number, our units are going to be radians per second. What do we get for, it should be 250. So 16 point, yep, got it. Thank you. 16.67 radians per second. Now, this is where we are solving for an angular velocity as our final answer. Yes, we get radians per second out of this equation, but we do not leave it in radians per second because it means nothing to anybody, okay? We're going to convert this to revolutions per minute. So even though we know that our W2 is 16.67 radians per second, we're going to convert it. So we're going to convert first 2 pi radians on the bottom is equal to 1 revolution. And then 60 seconds is equal to 1 minute. Okay, so seconds cancel. So we're left with radians, or I'm sorry, revolutions per minute. So we're going to take our answer, 16.67, multiply by 60, divided by 2, divided by pi. And our W2 final answer, what do we get? Did you say 259? 159. 159 point what? 15. Okay. And that's going to be in, and you can write this as RPMs. You don't have to write that revolutions on top, minutes on the bottom. Thank you, Jack. And then box around our final answer. Okay. The direction is given up here by your label. So make sure in the diagram that you label the 250 inches per second. That's VB. show the direction of W2 being clockwise and label W2, and then writing everything out here and converting your final answer to RPMs. Okay. So any questions on example 2? All right, this is fun. The next one that we have here is example 3. So we have a link, and it's a link that's like a triangle. Okay, so it's a single link rotating around point A, or, you know, this is affixed to the frame. This is link number 2. This is A. It says link above rotates at 15 RPMs clockwise. Okay, so this entire link is going clockwise. All right, at 15 RPMs. Okay, so what I want you to do is I want you to answer, see what you can do with the items that are down below. I want you to see if you can find or determine angular velocity of A, B, C, angular velocity 1 and 2, VB, VA, BB, VC, V1, V2. See what you can come up with those. Okay. In some cases, maybe it's like, that doesn't make sense. That's nothing. That's not what we would do. In other cases, you're going to be able to maybe see like, oh, this is what it is. So go ahead and fill in what you think those should be based on the information given. So I'll give you a couple minutes to do that, and then we'll go over it together. What do you mean?
All like one.
Yep, this is all part of one example. Is that what you're asking?
No, I have like the frame, have all the links.
This is just one link. It's not this is just link number 2. It's a triangle, and it has an endpoint B, C. So this is just rotating around here as a single link. Yeah, good question. Thank you. A solid object, yes. So that's why I kind of went like this. All right, even if you haven't gotten through all of them, we'll start going through them together. So, so the first one, the angular velocity of point A. Now, as we look here, point A is the center of rotation, so it is going to be fixed to the frame. So what do you think the rotational velocity of point A is, or the angular velocity? It's zero, right? It's zero. So this is going to be zero, or you might even say it's not applicable, okay? Either one, because it's center of rotation and it's affixed to the frame, so it's not moving. You would get a zero in the denominator because it would be a division by zero radius, right? Yeah. Now, the angular velocity of point B. Point B is on link number 2. And if you remember, all of the points on a link are going to rotate at the same angular velocity as the link. So since this point is out here and the link is rotating, what is its angular velocity? It's W. 15 RPMs, exactly. If you wanted to convert it, you could, but we can just leave it as 15 RPMs. What about point C? Also 15, yes. What about W1? 1 meaning link number 1, which is the frame. That's 0, yeah, no rotation or not applicable, right? But what about W2? The angular velocity of link number 2. 15 RPMs, yes, 15 RPMs. So we can say, just like we did on the previous example, this is equal to W2. That is the rotation of link number 2. Good. Those are all my W's. Straight line velocity V. Straight line velocity V. Straight line velocity is going to be the straight line velocity. And I like to think of it as, let's say this is rotating, 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 rotating around. And if I would stop suddenly, what would happen to that point if it wasn't fixed? So for instance, if this is rotating around and I stop suddenly, what happens to point B? Would it keep going or would it do something else? Okay, that's kind of what we're looking at here. So straight line velocity of point A. Point A is right there. What do we think? It would be nothing. It would be 0 because it is at the center of rotation. It's like neutral. It's not going to be going. The radius is going to be 0. So this is going to be 0 because that's the center of rotation. What about the velocity of B? Could we draw the velocity of B, straight line velocity of that? Yes, we could. As we said earlier, it's going to go in the direction of rotation, right? And it's going to be perpendicular to its radius back to the center of rotation. So here's its line, center of rotation, and it's going to be something like this, 90 degrees to that, and this would be VB, right? Now, to calculate that, how would I determine its value? I go back to the front page, V is equal to WR, right? So this is going to be WT times R out to B. I'm sorry, I said WT. W2 times R out to B. Now, the radius out to B, we can see, right? That's going to be 4 inches. But what about W2? I know I can't put 15 RPMs in there, can I? And because I don't have a ton of room here to put like the conversion right there, and we might have to do it for another 1 or 2, why don't we convert, actually show W2, so 15 revolutions per minute. I'm going to do that conversion up here, and we're just going to use our final number in our calculations. So we know that 1 revolution, 2 pi radians, And 1 minute is equal to 60 seconds. So minutes cancel. Oopsie, radians do not. Radians stay on top. Revolutions cancel. So I'm radians per second. So my W2, what do we get for that number? 15 times 2 times pi divided by 60, 1.2, 1.57. And that's going to be radians per second, radians per second. So that's what I'm going to use down here, right? So this is going to be equal to 1.57 radians per second times the radius from the center of rotation to point B, which is 4 inches. Okay. So I'm going to multiply those two. And what do I get for VB? $6.28-ish. 6.28 confirmed. Okay, great. And now when I multiply inches times radian, I end up with inches and then per second. So my final answer, so this would be VB, not W. VB is equal to 6.28 inches per second. That's its magnitude. And its direction is going to be down and to the right, perpendicular to the radius back to its center of rotation. Virtually, you guys doing okay? Does that make sense? Okay. Velocity at C is similar, okay? It is similar. So it is going to be, if we look at C here, this is rotating on that same link. Now, its velocity will go in the direction of rotation. The rotation is going to be clockwise. So our velocity at C, I'm going to draw it so that it's 90 degrees back to its center of rotation here. So 90 degrees to that radius of 2.5. So this would be VC. VC. So its direction would go like up and to the right. So again, if I'm rotating, I suddenly stop and C is not affixed to this link, it would continue in a straight line going up and to the right. So now down here, same equation-ish. W2, right, on link number 2 times the radius this time to C. So it's on the same link, so it's going to be the same 1.57 radians per second times 2.5 inches this time. So what will my value be? 1.57 times 2.5. 3.93, I heard from 2 people, and that's going to be inches per second is equal to the velocity of C. Okay. Questions on those two? All right. Velocity of point or of link number 1. It's the frame. That would be 0, right? What about straight line velocity of link number 2? No, we usually don't. We usually don't. It's usually your straight line velocities are going to be at like points on the link. So the link by itself, we can just put this is not applicable because it's a straight line velocity of a link. This is a rotating link, so it just has angular velocity. Okay. So any questions on example 3? Okay, make sure you have all the elements that are here. Awesome. This is fun, isn't it? Page 5. Okay. Just a little bit of a intermission, if you would. What I want you to do is I want you to write down anything that means anything for any one of these. So straight line velocity, tell me what equations, units, direction, how would you define it? And same thing for angular velocity, equations, units, directions. Just write anything that you think you know. I'm going to give you a minute to do that. Just, this is going to be for, yeah, just personal, and then we'll go over and make sure we have like kind of hit the highlights. So I first want you to take a crack at these items. You can look back in the handout as well. Okay. Okay, let's start looking at filling some of this in, or just making sure you have what you need. So straight line velocity. Straight line velocity is always going to be the V as its variable. So there was two straight line velocities that we saw. So the first one was rectilinear, where we're going to take, I'm going to use D for distance divided by time, whether it's an S or an R for D, but it's distance divided by time. Or the other one was, if it's on a rotating link, its V is going to be equal to WR, or angular velocity, times the distance that point is from the center of rotation. Units. What are the units that we're expecting for velocity? Inches per second, feet per second, meters per second, and so on. Okay. I'll just kind of put do. Anything that is distance divided by time. Now, direction. When it's rectilinear, it's going to be along its path. So I'm going to put rectilinear. Along path, which would be a straight line. So if it's horizontal, it'd be left or right. If it's vertical, up or down, or along a line. Okay. But if it's a velocity that is on a rotating link, it is going to be perpendicular to the radius in the direction of rotation. Okay. So straight line velocity V will always be perpendicular to the radius of rotation, pointing in the direction of rotation. Okay. Angular velocity. Any questions up here? Anybody have anything different or more or less, or wondering about what I put? Okay. Let's go down to angular velocity. Angular velocity, its equation, it's really the rearrangement of this relationship. W is equal to V over R, right? V over R. Units are going to be radians per second in and out of that equation, okay? You have to use radians per second in that equation. But we also will either get them or we have to deliver them in RPM when it's a final answer. Okay. And then direction is either going to be clockwise or counterclockwise. It's going to be rotating about a fixed point. Okay. Any questions there, or anybody have anything different or want to add or subtract? Okay. All right. Page 6. We have example 4 and example 5. Okay. Example 4, it says draw the velocities for point B on each one of the links. Okay. So for the first link, you'll notice that I guess we didn't label it link number 1, link number 2, but assuming that this is just a generic link, it is rotating in a clockwise direction. We want to draw the velocity, which is the straight line velocity of point B. So as we know, velocity is always going to be perpendicular to the center of rotation, and they will point in the direction of rotation. So that is going to be the velocity of point B for the first one on the left. The middle one is rotating counterclockwise. So our velocity of B is going to start at point B and it's going to point up and to the left, or I'm sorry, up and to the right. And it is going to be perpendicular to that radius back to its center of rotation. And that's going to be the velocity of B, straight line velocity. And then our last one is going in a clockwise direction. And based on the position of B, it's going to be going, if you would, to the left, perpendicular to that radius back to its center of rotation. How do I know that A is the center of rotation in each one of these? What is my clue? Huh? It's on the frame, right? A is that joint that has the frame around it, right? And this is our does not move link. Okay, so using what we've learned in the past, we're going to see that continue to be our symbol for something that doesn't move. Okay, any questions on example 4? Then example 5, this time we want to draw in the correct direction for our angular velocities this time. So in each one of these cases, we're given straight line velocity of point B, which is on the end of each one of these links. Okay. Now we want to add in our W and put it in the right orientation. So if we have the straight line velocity of B perpendicular to its center of rotation going up and to the right, then this link would be going in a clockwise direction. For our middle one, velocity of B is going up and to the left. This means that this would also be going in a clockwise. It doesn't have to be, I don't have it labeled as link number 2. So the W is going to be going clockwise as well. And then our last one, the velocity of B is going to the right on the link in this position. So that means our W is going to be going counterclockwise. And remember, W is angular velocity and applies to the entire link. Straight line velocity will be on an individual point somewhere or along that link. All right. So as far as the first part of the lecture, this was as far as I wanted to go for right now. Let's kind of go back to our PowerPoint presentation, which was on our handout. This is the last slide on there. I want to go back a level and let's take a peek at our practice problems. So as we look at our practice problems here, there are 3 things that you're going to be handing in. The first part is going to be example 6.1. That was the example that we looked at the very beginning of the chapter, and we wrote out, just the calculation for the rectilinear velocity of that crate that was on the conveyor. So you need to include that in your practice problems. The second part here is filling in the chapter 6 handout. We've gotten about, I want to say about halfway through. Okay, there's more that's coming. Relative velocity method is next. We kind of set the stage and got everything kind of the background stuff done today. So we're going to continue on in that handout. So that's not ready yet. And then we do have an additional example, 6.6, that we are going to be applying as well to the practice problems. Okay. Let's take a peek though. At the end of the chapter, I do have some things assigned that based on what we've done so far, you would be able to get started. So this is going to be at the end of chapter 6, our problem. So let me go to assignment 3. And there are quite a few problems, all right? So I'm just going to kind of peruse here. I just want to be sure I have them. So I've got 1, 2, 3, 4, 5, 6. And then we jump to 11, 12. Okay. All right. So the ones that you would be prepared to do are 12 and above. Okay. So about the first half, if you would. Okay. So let's take a peek at the end of chapter 6, starting on page 161. We'll look at these problems and just make sure that you have a good idea of what you're going to be doing for these. You'll notice that you do have answers in the PDF form here for all of the problems as well. So I'm going to go underneath. So on page 161, okay, the first problems that we have here, so 1 through 6, are going to be assigned. Now, these are going to relate to either rectilinear or conversions, okay? So let's look at the first one. It says we have a package is moved at a constant rate from one end of a 25-foot horizontal conveyor to the other end in 15 seconds, okay? I think it's just like that example 6.1 that we did, but the time is different, okay? Determine the linear speed of that conveyor belt, okay? So just like example 6.1. The next one here is we have a hydraulic cylinder that extends at a constant rate of 2 feet per minute. Determine the time required to traverse an entire stroke of 15 inches, okay? The next one is determine the average speed in miles per hour of an athlete that runs the 4-minute mile, meaning 1 mile in 4 minutes. How fast is that athlete going in units of miles per hour? That's a conversion, okay? The next is what is the average speed? I'm sorry, no. Determine the average speed in miles per hour of an athlete who does the 100-meter dash in 10 seconds. So 100 meters per 10 seconds. Just convert that to miles per hour. Number 5, a gear is uniformly rotates at 270 degrees clockwise in 2 seconds. Determine the angular velocity in revolutions per minute and radians per second. So that again is a conversion. You're taking 270 degrees in 2 seconds, and you want to convert that to revolutions per minute and radians per second. Number 6, determine the angular velocity in RPMs of the second, minute, and hour hand on the clock. Okay. So angular velocity in RPMs. Number 11, the problem statement is down at the bottom. Okay. It says the drive roller in or for a conveyor belt is shown in figure P611. That's up here, right here. All right. This is what it's referring to, figure 6P11. Determine the angular velocity of the roller when the belt operates at 10 feet per minute. So 10 feet per minute, that means that that's its velocity. So if we go up here, okay, here's the roller. All right, think of that as link number 2. Here's the center of rotation and the radius of that roller. This is a link number 2. What is its W? Okay, you'll notice that the velocity is at 10 feet per minute. So if we put it out here at the end, so think of this as link number 2 with a point B, like the problems that we did earlier. And then this is its direction of straight line velocity. And we want to know what is W, using that W is equal to V over R. Okay. And then you're going to be doing number 12 as well, using that same illustration above. Put it all in the same here. This time the drive roller for the conveyor that is shown, determine the linear speed of the belt this time when the roller operates at 30 RPMs counterclockwise. So in this case, we're going 30 RPMs counterclockwise, same direction. But if this is going 30 RPMs, how fast is B going straight line velocity? Okay, so that's going to be similar to the two problems. Examples 1 and 2. Very similar to those. Okay, out of the handouts. So, and then as we move to the next problems, those are related to relative velocity. So we will be talking about that the next time that we're together. Okay, so tonight, that is where I'm going to stop, and you'll have the rest of the time to work. So let me stop our recording.